I want to talk about trends in electron affinities as we move around the periodic table. And I want to start off by pointing out to you that if we look from the top to the bottom of the periodic table, we might expect, and keep in mind what we're talking about with electron affinities, we're taking a neutral atom and we're adding an electron to it. You might expect as you move down the periodic table, you're adding that electron to an N shell that is further from the nucleus, so it might be less favorable to do that. And that actually doesn't hold very well for electron affinities. It holds well for the alkali metals in the first column, but for a lot of other things it doesn't hold nearly as well. And I'm not going to talk about why there is that variation from what we expect. What I want to focus on is going from left to right across the periodic table, because that does match what we would predict. And you might expect as you go from left to right across the periodic table, it would get more favorable, more exothermic to add an electron to a neutral atom, because the effective nuclear charge increases from left to right across the periodic table. And that is the case. You'll notice lithium is -60, whereas fluorine is -328. But there are some exceptions, and I want to talk about why those exceptions exist. First, if we compare beryllium to boron, you'll notice that beryllium is actually less favorable than boron. Actually, I'm sorry, I want to talk about looking in the other direction. Beryllium is less favorable than lithium. And you would expect the opposite. And the reason for that is if you think about where you're adding an electron to. For beryllium, you have the 2s subshell completely filled. The electron you add is to the 2p shell, which is a little bit further away than the 2s shell from the nucleus, and therefore a little less favorable to put an electron in. Likewise, when we get to nitrogen and we compare it to carbon, there is an exception or a variation from what we would expect. And that's because if you think again about what you're doing when you add that electron to nitrogen, at nitrogen you've half filled the p shell. You've added an electron to the px, the py, and the pz. The next electron that you add to nitrogen for the electron affinity goes into a p shell that's already half filled. So the electron is paired now. And paired electrons repel each other a little bit, making it less favorable to put an electron there, which is for the why we see the variation with nitrogen. So the differences from our general trend of getting more favorable going from left to right across the periodic table come when we have a filled subshell, and the next electron we add is to the next subshell, the first electron in the next subshell, in this case going from S to P, or if that subshell is half filled and you're going to start pairing electrons, as we see when we go to nitrogen.